boundary condition is satisfied. So if you look at this equation, right? If this a curl of E has to be finite. What does curl of E have to be finite? It means that tangential E has to be continuous, because if you look at an interface, if the electric field is pointing in that direction for this component, curl of E is something that you take the derivative in the normal direction, okay? And this has to be continuous in order for curl of E to be finite. So immediately by staring at this equation, you know tangential is continuous. And then you look at the second one, the curl of this thing must be continuous, then the tangential component of this has to be continuous. And that actually means tangential H is continuous, because mu inverse curl of E is tangential H. So you don't have to go through the derivation. And just eyeballing the equation, you see the boundary conditions. Okay? So let's go back to this problem that we are solving. And we want to study reflection from a half space. And this is actually a very simple problem that you probably have studied it before in your undergraduate course, say epsilon 1, mu 1, epsilon 2, mu 2. And that we have an incident wave, a reflected wave, and then a transmitted wave. And in your undergraduate course, you probably set up this as a plane wave incident, plane wave reflected, plane wave transmitted. But what I'm saying here is that it can be reduced to a 1D problem. Okay? Because I only have 1D equations to solve from now. An incident wave and the reflected wave and the transmitted wave. And the 1D equations are the 1D ordinary differential equations that you saw a little while ago that I have erased from the blackboard. Okay, the 1D ODE looks something like this. Y equal to 0. So this can be reduced to a 1D problem. Hence, we are going to solve this problem slightly differently from what you did from the undergraduate course. Another way of looking at this problem is that this 2D problem can be mapped into a 1D problem. And this 1D problem is actually analogous to a transmission line problem. So all these problems that you have are analogous to the one-dimensional transmission line problem. So let's see how we can set this up for the TE case. EY is equal to EY e to the I kxx case. And because it becomes a 1D problem, so we would have E1y in this region, E2y in this region. Then the boundary condition is that E1y is equal to E2y. Let's assume that this is Z equal to 0. And that because in region 1, we would have a solution that looks something like this. E to the I k. We can throw out the kx term actually. E1y must be something like e to the I k 1 z z with a certain amplitude. Let me see what I put. I put E naught as my amplitude in my notes. And then there should be a reflected term. The reflected term must be something of this form. This must be the solution in region 1. The solution in region 2 must be just a transmitted wave, I k to z z. Okay, so represent the wave that goes in a negative z direction. I'm using e to the minus I omega t time dependence in this course. Let me remind you of that again. And then we mesh boundary conditions. Boundary conditions are E1y equal to E2y at z equal to 0. So if we match these two boundary conditions at z equal to 0, I get 1 plus r equal to t. Okay? And then the other boundary condition is this one that I just have slightly erased, which is that over there. If I impose the other boundary condition, I will get k1z over mu1, okay, with a minus sign over there, times E naught plus k1z over mu1 times r, which is what I have for the second term over here, must be equal to minus k1z, k2z over mu2t. So these are the two equations. And then I can rewrite the second one as k1z over mu1, 1 minus r, is equal to k2z over mu2t. And of course the one is this one. You can solve this equation for r and t, and this gives rise to the famous Fresnel reflection coefficients. Okay, you get r is equal to mu2 k1z minus mu1 k2z over mu2 k1z plus mu1 k2z. Okay, these are called the TE reflection coefficient, and oftentimes we just add a superscript TE, and then TTE is 1 plus RTE, which is 1 plus this, and this gives me 2 mu2 k1z okay, so those you have derived before in your undergraduate courses. And you can repeat for the TM case. TM case, you go to the same exercise, you will obtain that RTM is equal to epsilon 2, because you will have epsilon involved in the boundary condition. Epsilon 1 k2z over epsilon 2 k1z k2z. Okay? And then TTE, TTM is just 2 epsilon 2 k1z over epsilon 2 k1z plus epsilon 1 k2z. Okay? So any questions regarding this? This is undergraduate stuff. I'm just repeating the derivation using a different perspective. Okay, these are the famous Fresnel reflection coefficient, first derived in the field of optics, I believe. So you could have arrived at the second one using duality principles as well. You can invoke duality and arrive at this second equation using duality principle. If you don't want to rederive them from scratch. But what kind of physics are embedded in this Fresnel reflection coefficient? First, there is the physics of total internal reflection. And that occurs when K2Z becomes pure imaginary, that the wave in region 2 becomes purely evanescent. Okay. So K2Z, in this equation K1Z, if you remember, K1Z is equal to this. I'm sorry to not elaborate on this. This is actually KZ squared. Okay, this thing minus this thing is KZ squared. And if you write down the solution, then equation solutions in region 1 and region 2 are according to this. So K1Z would be equal to K1 squared minus Kx squared K2Z would be equal to K2 squared minus Kx squared. The Kx's and each region has to be the same. The Kx have to be the same. What principle is that? What? Phase matching, okay? So we keep Kx to be the same so that the boundary condition could be satisfied. If the Kx's are not the same, then these two waves will have different phases. Then boundary condition cannot be satisfied, okay? So the Kx's have to be the same. And there could be an occasion where K2 is less than Kx. You can set up an incident wave so that this K vector has Kx component as well as Kz component. Okay, but then its Kx component can be larger than the K vector or the wave number of region 2. In this case, then, sorry, this should be K2 squared. Okay, then K2Z is negative. K2Z squared is negative, implying that K2Z, which is square root of K2 squared minus Kx squared, is purely imaginary. This may be something like this, I alpha 2. It becomes a pure imaginary number. If that is the case, then you can see that if K2Z becomes pure imaginary, RTE would be mu2 K1Z minus mu1 I alpha 2 divided by mu2 K1Z plus mu1 I alpha 2. So this is the real number, this is the real number, assuming that everything is real. So this thing is of the form of A minus IB over A plus IB, which means that the numerator and the denominator are complex conjugate of each other, which means that if you were to take the magnitude of this complex number, it's always equal to 1, because it will be magnitude of this, and magnitude of this is magnitude of denominator or numerator over denominator. Okay? And they're the same. Means they're just the complex conjugate of each other. So the reflection coefficient will always have amplitude of 1. This means that the energy is totally reflected, because energy is proportional to field squared. So if the reflection coefficient is 1, the energy would also be totally reflected, and this is known as the phenomenon of total internal reflection. That happens in the case when this can only happen if K2 is less than K1. That region 2 is optically less dense than region 1, which means that if a wave comes in, because this is optically less dense, the wave is refracted in this manner. Okay? So if you keep increasing the angle of incidence, then there will be one juncture that the transmitted wave will be horizontal. And if you go beyond this thing, then the wave will be totally reflected. This angle is known as the critical angle. The angle at which the wave will become horizontal and then totally reflected. And then what happens then is that if you go beyond the critical angle, the wave will be totally reflected, but then you only have evanescence wave on the transmitted region. The wave becomes exponentially decaying and becomes evanescent, and no energy can be transmitted, and energy can be reflected. Okay. Any questions regarding this? What kind of power is actually flowing in region 2 in the case of total internal reflection? What kind of power is flowing there? Reactive power, okay. If you study this problem, which I don't have time to go into, you study E cross H conjugate. You will find that there will be real power flowing downward when there's no total internal reflection. But in this case over here, you study this power, it becomes pure imaginary. There's no real power anymore. Okay, this is known as reactive power. And you can probably just learn not too long ago, that if we have E as a function of time crossed with H as a function of time in the time domain, this is half the real part of E crossed with H. In the phasor domain, where these are all phasor quantities. Okay? So if this thing becomes purely imaginary, these are phasors, there will be no real power flowing, and there's only imaginary power flowing. And this these are known as reactive power. These are known as reactive power. Does everybody know the concept of a reactive power? What is the reactive power? Aditya, do you know? What is reactive power?
The difference between the power stored in the electric
Yes, that can be thought of as the reactive power.
They oscillate back and through, so they do not propagate away. They just temporarily transmit in that way.
Right, it's actually corresponding to energy stored in the field. And the energy does not flow. Okay. So you have this kind of example in circuit problem. You also have this. Let's see how can we set up a problem in circuit so that this is true. I think this will show the notion of reactive power. So you have a current, you have a voltage, which are phasors. You have an impedance. I use circuit notation, okay, so that V is equal to J omega L I tilde. So power, complex power is given by this quantity over here. Is given by J omega L I conjugate. And this is a pure imaginary number. So in this circuit, the only power you have is pure imaginary. Okay, so there's no real power flow in this circuit. But then you can also set up a situation where there is both the existence of real and reactive power by putting in a resistor, so that some power will be dissipated, and in this case, I would be equal to V tilde over Z, and Z is equal to J omega L plus R, right? So you can say that V is J omega L plus R I, and that is equal to so in this case you can show that there will be both real and reactive power flowing. Okay? And if you go and study V cross I now, it's not purely imaginary. It will be having a real and imaginary part. So reactive power can be thought of as the power that's flowing in the stored energy of the system. If you look at this term here, if you analyze that system, that would also be true. You find that reactive power is somewhat proportional to the stored energy of the system. So when you have this kind of system that stores energy, it consumes reactive power. Okay, that is something that you should learn. Okay, let me not go into this. You can learn about reactive power from the power engineering folks. They worry about this quite a bit. Because when you run your washing machine, your dishwasher in your house, it has motors. Those motors are big inductors. Those inductors give rise to reactive power. And the power has to be sent to your home and then taken back to the power company. But then when it gets sent to your home, it's sent over power line that have copper loss. So the power company still charge you for that, even though this is imaginary power. Okay, sends it to your home and then take it back, send it to your home and take it back. But take it back to the copper line, the power line that has copper loss. Okay, so you still have to pay for reactive power. So if you run a lot of big machines that have big inductors, it's expensive to run them. Okay. So another thing I like to point to you is actually Brewster angle. This exists for RTM. Okay, RTM occurs as such. RTE, this is usually replaced with mu, but most materials are non-magnetic in this world, so they're not that easily observed for TE polarization, but quite prevalent for TM polarization because most materials have epsilon 1 not equal to epsilon 2, but it could occur that there will be certain angle of incidence that this is equal to each other. If that is true, then the reflection coefficient will be equal to 0. So if you plot the RTM as a function of angles, say this is 90 degrees, this is 0 degree. There could be an angle in between, known as the Brewster angle, where the reflection coefficient goes to 0. Okay, this is RTM. RTE will look something like this. This is a magnitude. Okay, it will look something like this, and it could not. If this is not there, that would be the case for RTE. It would be something just like K1Z minus K2Z over K1Z plus K2Z. So most materials are non-magnetic, so the mu cancels out, and then RTE will look something like that. And you can see this effect with your sunglasses. If you go to a shop and buy sunglasses, and if they're good polarizers, they will try to reduce glare. Okay? How do they reduce glare? It's because if you have a sunlight propagating, say if you are in the driver's seat in the car. Okay? You see two kinds of light. One is direct light from the object. The other one is the reflection of the ground surface. And these lights are randomly polarized. But the reflection of the ground surface, after it has gone through this process, it will be TE dominated, right? Only the TE field will be dominantly reflected. The TM field is reflected less. So the reflected field will be TE dominant. So if you drive in the car and look at the road, all the reflections on the road surface are TE dominant. So how do you remove the glare from the road surface? You make sunglasses that are kind of allow only vertical polarization to go through. You put in a vertical polarization in your Polaroid glass, and then only vertical polarizations can go through. And then you will reduce the glare from the road surface. So this can be. So next time when you go and shop for a pair of sunglasses, do a test with them to see if they do reduce glare. It's very easy to do. You just, in Walmart, you take the sunglasses off the shelf, and then just rotate them and look for the reflection from the floor surface. If there's no dimming as you rotate the sunglasses, those are no good sunglasses. Okay? But if they do reduce the glare from the reflection from the floor of the Walmart, those are good sunglasses. Okay, so you can use this principle to study that. Any questions on the Brewster angle? But there's another very interesting phenomenon, very close to the Brewster angle physics, okay? Which is that when the denominator goes to 0, can the denominator ever go to 0? We studied Brewster angle for the case when the numerator goes to 0. Can the denominator ever go to 0?
The interface of some metal that epsilon is negative or something.
Very good. If either epsilon 1 or epsilon 2 is negative, then that's possible. Those are called epsilon negative material. Okay? Let me see. Epsilon negative material. So then epsilon 2 k1z plus epsilon 1 k2z can be 0, right? Because one of this is negative. Then there's a chance for these two to cancel each other. Okay, this could be positive, this could be positive. One of this is negative. And where can you find epsilon negative material?
Plasma.
Yes?
It's metamaterial, you have to make it.
Metamaterial is one that people try to make artificially. How do you find naturally occurring epsilon negative material? Do you know? Okay. You know, right? You probably know.
Metals.
Metal, okay. Gold and silver. Gold and silver, okay. Yes?
I thought they were complex.
They're complex, that's right.
So the real part is negative.
Right, right.
And they have, but the complex.
You have a lossy term.
So the complex component has to be as well.
Right. So the cancellation is not perfect, but quite good. Okay? Yes, Kurt, you have a question.
If one of them was negative, then the corresponding k term would be imaginary, wouldn't it? Because that's square root of that term?
Well, it turns out that when that happens, both of these two become imaginary. Okay, both these two terms become imaginary. This is positive, this is negative, and they cancel each other.
It would only be imaginary if both materials had a negative sign.
Right, so you can have a situation where k1z is k1 squared minus kx squared. K2z is k2 squared minus kx squared. And then let's assume that one of them is epsilon negative. Let's say epsilon 2 is negative. Then what happens here is that if this is negative, then k2 squared is negative. Okay? Then this whole thing becomes imaginary. Let's assume that this is positive, but kx is larger than k1 to make this pure imaginary. So this one does not have to be epsilon negative material. This one could be, but then you can have a situation where this is pure imaginary, this is pure imaginary, and since one of them is negative, they will cancel each other.
So it's only for evanescent waves?
For evanescent wave. So for this kind of situation, the wave is evanescent in both regions. Okay, because K1z is pure imaginary, K2 is pure imaginary, and then epsilon 2 is negative, epsilon 1 is positive. Then you can have this mode existing. And you can solve for it. And you can solve for this equation. When could this happen? Okay, this could happen when this is true. And of course, this equation cannot be solved, so you square it to solve it. K1 squared minus Kx squared is good. Epsilon 1 squared, K2 squared minus Kx squared. And then you can solve for Kx. I won't go through the details, you can do that yourself. But it's exactly the same as the Brewster angle condition. Because if you do the same to the numerator and solve it, you cannot solve this equation other than to square it. Because you square it, you remove the minus sign. So the equation you arrive at for Brewster angle is exactly the same equation you arrive at for the surface plus one mode. But this mode makes the denominator go to 0. The Brewster angle makes the numerator go to 0. This is amazing and confusing, isn't it? In one case, the numerator goes to 0. In another case, the denominator goes to 0. And it takes a lot of time for you to sort out why this difference. Okay, but I will not go into detail of this until later on. We'll learn about branch cuts and Riemann sheets. This mode, the Brewster angle mode and the surface plasma modes are actually on different Riemann sheets. Okay, you wouldn't be able to sort this out at this point until you learn about Riemann sheets. Okay, but you can see that I can have a condition where the denominator goes to 0 for epsilon negative material. I can have a condition where the numerator goes to 0 for epsilon positive material. Okay, and the epsilon negative material would have a mode that looks something like this, call it surface plasmon mode. Or some people call it SPP, surface plasmon polariton mode, or surface plasmon resonance, or surface plasmon something. There are lots of names associated with white plasmon. Well, you probably learned that if you have a plasma medium, the dispersion relationship looks something like this for a simple plasma. This is called a cold plasma. A plasma without loss. And if omega is less than omega p, then this is epsilon negative. Okay? And of course, there's no such a thing as a cold plasma. All plasma have a certain amount of loss due to collision. The electron collide with each other. So this is only the ideal case. So what I'm talking about here is the ideal case. As I mentioned before, there will be some loss. For gold and silver, you will have something like epsilon is equal to something, maybe some negative number plus some loss somewhere. Okay? This loss is due to collision because at high optical frequencies, the sea of electrons that you see in the metal, that sea of electron behaves like a plasma. Okay, but it will have collision and it will give rise to losses in the system. Okay, but in order to understand this in a very simple-minded fashion, we can assume no loss. And if you assume no loss, then you can understand surface plasma quite easily. And then you can always put in loss as a perturbation. And the physics will not be drastically changed. Okay? Are there any questions regarding this?
Yeah, for the reflection coefficient, they may be somehow large, but they are confined by the skin depth of the interface.
Right.
So it is still physical, right? According to the
Right. It wouldn't exactly go to 0. This actually makes things happier because if this thing does go to 0, it means that reflection coefficient is infinite. That's not physical. Right? So reflection coefficient will only show a peak when you hit the situation where these two cancel each other. Okay, you see a reflection peak, but not an infinite peak, which is not physical. So it will have a finite peak due to losses in the system. Any questions? Okay, if not, we'll move on, because we come back to surface plasmon later on when we understand Riemann sheets and so on. Riemann sheets and so on, and then you will enjoy learning about surface plasmon more when you learn about Riemann sheets. Okay. So, let's study now the reflection and transmission through multi-layer. That if we have, this is actually analogous to a transmission line problem. That if we have an incident wave propagating to this, and if we have a plane wave propagating to this, how do we study for the solution of this? This problem can be set up very easily. Like I can do the simple case of a 2-layered medium or 3-layered medium, depending on how you call it. And I can call this Z equal to minus D1, Z equal to minus D2. Okay? And then I can write down the solution in region 1. Let's call this region 1, 2, and 3. I can write down the solution in region 1 first, as E1y is equal to A1. So this represents the incident wave. It will have, I solved this as a 1D problem because I say all these problems can be reduced to 1D. I can